So decision problems related to context-free grammar. Usually decision problems are problems that will be answered with either yes or no. We'll have yes or no answers for decision problems. So what are the examples of decision problems that are related to context-free grammar? That is what is the focus of this video. Already we have seen decision problems related to context-free grammar, and we have seen check whether a given grammar is ambiguous or not. If you have two or more rightmost derivation or two or more leftmost derivation, then we say that grammar is ambiguous. If this condition fails, then it is not ambiguous. Already we have seen problems related to check whether a given grammar is ambiguous or not. We also know next decision problem is to check whether a particular string belongs to the language generated by the grammar or not. If the start symbol of this grammar is yes, if we are able to derive x using the grammar applying one or more times the production rules, then we say that x belongs to language generated by grammar. So if you are not able to derive this x from the start symbol applying this grammar, then it does not belongs to L. This is also not new for us. We have seen this type of problems. This comes under decision problems related to context-free grammar. Now, to check whether a given grammar is empty or not, what does it mean by empty or not is, if this grammar generates terminal symbols, then it means that it is non-empty. Any grammar from the start symbol, if it is able to generate terminal symbols, then it is non-empty. Otherwise, it is empty. Okay. And you have one more decision. These are examples. We have other decision problems also. I have just described these examples here. So one more example we are going to see is to check whether a given context-free grammar is finite or not. So we'll try to give examples for third and fourth one. Now here I have taken one example. Check whether the grammar is empty or not. We have given with a grammar. So we have to check whether the given grammar is empty or not. From the start symbol, if you are able to derive terminal symbol, then this is not going to be empty. So here we have set of 5 productions, out of which the C is already generating a terminal symbol. So let us substitute C goes to D in whichever production that is having C. C A is having, B is having, and D is having. So in A production, B production, and D production. In these production, let us substitute. So it will be A, B, or D. S goes to, and A goes to. So instead of C, we will be substituting its right hand side. Again, B is BD, C is D, and D is equal to D and small d and capital D, terminal symbol. Now, by substituting C, we have arrived at another terminal symbols from B. Now, substitute, this is our first step. Now, substitute B goes to, what is BD, right? BD in whichever production that is having B. Now, S is having B, A is also having B. Now we will substitute here. So S goes to A, B, D, or D. A goes to A, B, D. Again a D was there. B goes to BD. C goes to D. And D goes to D and capital D. Now after substituting this B terminal symbols in A, we have another set of terminal symbol that is generated from A. Substitute this A in S. So if you are going to substitute A in S, we will be getting S goes to A, B, D, D. For this A, B, D, D we are replacing. Again a B, D and a D is there. A goes to all other production will be one and the same. Now by substituting A in S, we were able to derive a set of terminals from the start symbol. So S is able to derive A, B, D, D, B, D. Okay, so these are terminal symbols. These are terminal symbols. So from starting from S, we are getting some terminal symbols. So we can say L is, the language given is not empty. So when will we say that the language is not empty? When we are able to generate terminal symbols from the start symbol, then we can say that this L is non-empty. We were able to generate this set of terminal symbols from this S with the help of other productions also. So we say L is non-empty. Now for the fourth example, to check whether a given grammar is finite or not, we will take one more example. See, when will we say a language generated by the given grammar is infinite? Okay, we will say the language generated by the grammar is infinite if there is at least one cycle in the directed graph, generated from the production rules, of grammar G. We will say the language generated by the grammar G is infinite if there is at least one cycle in the directed graph generated from the production rules. We will see how to generate directed graph from the production rules. Okay. Now we'll take one example. We'll take a grammar. First we'll take this grammar. S goes to AB. Okay. And A goes to SC or A. B goes to SC or A. C goes to AB. Now to generate a directed graph, we have to verify whether grammar is in Chomsky normal form. That is the first step. Only then we can generate directed graph. Okay. Now this grammar is in Chomsky normal form because all the production is of the form a single non-terminal tending to two non-terminals or single non-terminal tending to a single terminal. So this is the rules. This is how the production rules should be for Chomsky normal form. So this production, all these production are already in Chomsky normal form. Now how to give the directed graph? So from S you have to give link for A and B, because from S you can derive A and B. From A you can derive S and C. Okay. From B you can derive again S and C. Now from C you can derive A and B. So accordingly you have to give the links like this. So in this particular directed graph, it contains cycles. It contains many cycles, right? It contains cycles. So given grammar is not finite, or otherwise is infinite. It is having cycles. See, from S to A to S, S to B, B to S, again A to C, C to A. Likewise, it is having many cycles. Even if it is having one cycle, then we say that the grammar is infinite. Now we'll try and check one more problem for this one. Second one.